In 1.10, we're going to look at different types of discontinuities, and you've seen these all before. So we're just going to reconsider them in terms of limits. Okay, the first kind of discontinuity is a removable discontinuity or a hole. Okay, it's removable because if I took out that one point, this would be a completely continuous function. So it's just that one point that's causing a problem. Okay, for a hole, the limit behavior we're looking at that tells me that this is a hole, let's call this graph f of x. In this case, the limit as x approaches 2 of f of x, where the hole is not equal to the actual value of f of 2. In this case, the f of 2 doesn't even exist, but f of 2 could be up here or something like that. So that's what happened at a hole. The next one is a infinite discontinuity. I can see the discontinuities here. It made an asymptote. Okay, in terms of limits, what does this mean? This means the limit as x approaches 3 of f of x. It does not exist. Why? Because it's infinite or unbounded. And that's why it's called an infinite discontinuity. And again, this happens at vertical asymptotes. Okay, the next one's a jump discontinuity, meaning, okay, I'm continuous on this graph until I get to 3, and then at 3, this is jumping up to the next point way up there. So in this case, the limit as x approaches 3 from the negative side of f of x is not equal to the limit as x approaches 3 from the positive side of f of x. It's jumping to a completely different value or jumping down to a completely different value. Okay, let's go ahead and look at some functions and figure out where their discontinuities are located and what type of discontinuity they are. And you did this probably in Algebra 2 as well. Okay, let's look at this one. Okay, this is rational. So there's going to be some kind of discontinuity where the denominator makes it 0, probably. Let's go ahead and factor it and simplify it. This is x minus 6 times x minus 2. X plus 5 over x minus 2. Okay, the first thing I notice is that I can cancel out x minus 2. Since I am canceling it out, it's a removable discontinuity or a hole. Where does it occur? It occurs at the value that makes this 0. So in this case, at x equals positive 2. So at x equals 2, there's a hole or a removable discontinuity. You can use those interchangeably. And it's just asking me where it occurs, so I'm not going to actually write the ordered pair. Okay, let me go ahead and write this simplified version of this function. It's x minus 6 over x plus 5. And if I notice, there's still another discontinuity because at x equals negative 5, where the denominator will become 0, there's going to be an infinite discontinuity, which is a asymptote. Okay, so at x equals negative 5, there's a vertical asymptote. Which could also be called non-removable discontinuity or an infinite discontinuity. And those words are kind of used interchanging. That's not the word. Those words are used alternately, so just make sure you understand that they're always the same thing. Okay, let's go ahead and look at B. It's rational, so I'm going to factor it and see if anything will simplify before I try to find if there's an asymptote. Let's see, x plus 1, that's a difference of squares. So this is x squared plus 1, x squared minus 1. X squared plus 1 doesn't factor more, but x squared minus 1 does because it's a difference of squares again. Okay, right here I can see that I can cancel out the x plus 1. Since I can cancel it out, I can remove it. So at x equals negative 1, there's a hole, or you could say there's a removable discontinuity. Okay, what am I left with after I do that? Let me write over here. I have 1 over x squared plus 1 times x minus 1. From the x minus 1, I know there's going to be an vertical asymptote. Or you could say an infinite discontinuity. Okay, now what about the x squared plus 1 situation? Let me set x squared plus 1 equal to 0 and solve for the x value that will make that the denominator 0. So x squared equals -1. If I square root both sides there, I'm going to get an imaginary number. So that's not going to produce any extra asymptotes than the one I have. Okay, let's look at 2 more. Okay, h of x equals the tangent of 2x for 0 is less than or equal to x is less than or equal to 2 pi. Okay, in my head, I know the tangent graph does have asymptotes, so there's going to be asymptotes. I'm going to rewrite the tangent of 2x as the sine of 2x over the cosine of 2x, so I can remember where the discontinuities are at. Okay, so what's the problem? I don't want the denominator to equal to 0, because that will make this undefined. So this is going to be undefined when the cosine of 2x is equal to 0. Okay, so I just needed to figure out when the cosine of 2x is going to equal to 0. Okay, now I'm thinking in my head, okay, if the cosine of 2x equals 0, the cosine is equal to 0 at pi over 2 and 3 pi over 2. Okay, now if I'm solving for x, I'm going to divide by 2, and then I'm going to come back because I need to think about this more because this is not as straightforward as it looks. Now, if I want to solve for x, I would divide by 2 or multiply by half, which means that x is at pi over 4 and 3 pi over 4. Okay, then I'm going to come back up here for a second. They want to know all the discontinuities from 0 to 2 pi. So 0 and 3 pi, pi over 4 and 3 pi over 4 are between a 0 and 2 pi. So they're both good asymptotes. But did I get all the asymptotes? No, I didn't. Pi over 2, 3 pi over 2. If I keep going, I could go to 5 pi over 2. Now, why am I listing 5 pi over 2? 5 pi over 2 is greater than 2 pi. 5 pi over 2 is greater than 2 pi, but when I divide by 2, this goes down to 5 pi over 4, which is still within 0 to 2 pi. So let me keep going to make sure I've gotten all the answers. So I've got pi over 2, 3 pi over 2, 5 pi over 2. Let's try 7 pi over 2. Okay, 7 pi over 2 is higher than 2 pi, but when I divide it by 2, it goes down to 7 pi over 4, which is still within the restriction 0 to 2 pi. Now, what if I kept going? I had 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. I would have 9 pi over 2. If I divide that by 2, I get 9 pi over 4. 9 pi over 4 is bigger than 2 pi, which means it would not count. So there's 4 vertical asymptotes, and I listed them all. Okay, let's go ahead and look at the last one. Okay, it says f of x equals x squared minus 1. There's no denominator, so I don't think there's an asymptote. I can't think of any asymptote. What would this be? This would be a parabola. Okay, so this is a totally continuous function, so there are no discontinuities. Because x squared minus 1 is a completely continuous function for all real numbers.